There we go. Hello and welcome to United Astronomy Clubs of New Jersey. Now it looks like a couple people still are going to make their way down and situate themselves and find their seats. So I do want to welcome you here to UACNJ. We are in Hope, New Jersey in Jenny Jump State Park. A few of you might be here because you're camping over in the state park. We do appreciate our state park. It's a great place to visit. But while everyone's just settling down, also want to say hi to our online viewers because that's right, we do live stream these to both YouTube and Twitch. So if you happen to be free on a Saturday night at 8 p.m., do feel free to check out us there, say hi in chat, or check out any of our presentations. I do want to encourage everyone, if you haven't already, do check out our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, all our past talks with links to view them, so you don't have to worry if you're like, man, I really wish I hadn't missed that talk on the Fermi paradox. Don't worry, we got you covered. They're saved on our YouTube. But in addition, you'll also find links to all our member clubs because that is also... We are a club made up of other clubs, and one of the easiest ways to get into and learn about astronomy is actually joining your local club, not only for ease of access, because I know some of you might have driven from pretty far away, but as well as the fact that they might have some tips and tricks for you, or events that are relevant to your interests, because the tips and tricks I know for viewing out here in Warren County, New Jersey, aren't necessarily the most helpful for someone who lives in New York City, just from the light pollution. But all of those are great resources to look at. In addition, you can keep in touch with us, ask any questions, find out what's coming up for our next presentation, all on our social media, our Facebook, our Instagram. We have a Discord server. Like I said, great places to ask questions. Share your astrophotography if you're doing that. I know a couple people a couple weeks ago had shared their images of the full moon, and that was neat. Now, for the people here, and I'll probably go over this at the end as well, there is a safety briefing. If you need to use the restroom, that is the porta potty in back. It is big, it is blue. When it gets darker, you'll see that is illuminated by red. We do have red lights here to try and direct you towards various things, as it doesn't mess with our night vision quite as much as any other colored light or white, even worse. We also have a little museum area and gift shop. I will be manning that area after the presentation because they will not allow me here to break the law of physics and be in multiple places at once. If I could, I would, but unfortunately, they won't let me. That being said, speaking of our night vision, any flashlights or if we're using our phone to get around in the dark, because we are in a state park, it will actually get dark. Do try and keep those pointed towards the ground and be mindful that we don't want to accidentally blind other people with the new latest, greatest 100,000 lumen flashlight we got off of Amazon. It's quite painful in the dark, and I spent the last half of the night walking around hoping I didn't bump into anything. That being said, do use your headlights when you leave. We prefer not getting run over. Using your headlights will help achieve that goal. So not only can people see that you are moving, but also you can see that you should not be running over people. This is not Frogger. It is not 10 points for every pedestrian. I heard a chuckle, so at least someone likes dark humor. With that, you're actually not here to hear me blabber on. You're here to hear our tonight's talk, which is about the James Webb Space Telescope, given here by Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1965. Just yeah, a little bit ago.
85. That's okay. I'm old, but I'm not quite that old, but I'm getting there.
I think I mistyped that. I need to correct that. I am sorry, Walt.
It's the first time you said that, so we're cool.
So, but he got his telescope just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and Rockland Astronomy Club, and he's been volunteering here at Jenny Jump for well over 20 years. With that, here's Walt.
Thank you. And welcome. I'm not going to mention about what a beautiful night you've picked because I've been known to bring thunderstorms with me.
Don't jinx
so
it.
Yes, that's exactly. So I'll try to behave myself, but it looks like we're going to have a great night. What I'd like to talk about is the James Webb Space Telescope and give you a 3-year update. This is the third one I've done. I started when we had 1 year of images, and the James Webb was launched on Christmas Day 2021, and it cost us $10 billion as taxpayers. Joint project between NASA, ESA, the Canadian Space Agency. And the first 5 images from James Webb was released on July 12th of 2022. So July 12th of this year was its 3-year anniversary of doing science. The time between Christmas and July, it was flying out there, and it was setting itself up, which was quite an involved process, much more involved than the Hubble Space Telescope. So we're going to take a brief look at some of the discoveries and new images that have come out in the last year, and take a look at the scientific impact. There was a lot to choose from, so it's very much whatever I felt like talking about. I picked a few. I tried to pick some that were representative of the type of science that the Space Telescope was meant to do. One of the big things is to gather information on the most distant galaxies so we can get a better understanding of how galaxies form, and also get an idea of if our guess on the age of the universe is correct, or if we made a mistake there. Look at star formations, search for exoplanets, some really good stuff out there, but it was really specialized to take images of very dim and distant objects. Now, telescopes are actually time machines. Does anyone understand how that could be? Well, if I take a look at an object, a galaxy, 1 billion light years away, I'm looking at light that took 1 billion years to get to my eye. And that means that the object that I'm looking at through my telescope may not even be there anymore, because I'm looking at it as it was 1 billion years ago. And when we hear talk about finding a galaxy that's 12 billion light years away, what we're saying is we're seeing the light from a galaxy only about 1 billion years after we estimate the Big Bang. We estimate the universe to be 13.8 billion years old. And so if we're looking at an object 12 billion light years away, we're looking at an object as how it appeared a lot closer to the beginning of the universe than it is to now. The James Webb is very different than the Hubble. The Hubble still looks like a telescope. The light comes in the tube, it bounces off a parabolic mirror, hits a secondary mirror, and then goes into an instrument box which records the data. Most of the observations on the Hubble were done in what we call visible light, and I'll get into that a little later. The James Webb doesn't really look like a telescope, but it certainly is. It's got the same elements. It's got a big parabolic dish. The light comes here, concentrates, goes up to the secondary, and then goes through that little slit where the instruments are located. And the James Webb records data entirely in near infrared and mid infrared. So in the areas of light that we can't see. The Webb's primary mirror, the big one, is 25 square meters, which is almost 270 feet. The mirror is broken up into 18 segments, as you can see, with a focal length of 131.4 meters. The mirror is made of beryllium, and it's plated with gold. And as big as that 25 square meter mirror is, it only takes 48.24 grams to coat that entire mirror. So that's less than 2 ounces to coat the entire mirror. Very, very thin coating. The James Webb Space Telescope has 6.25 times the light collecting power as the Hubble. Here's another huge difference. The Hubble orbits the Earth at about 355 miles. So we sent a space shuttle up to deploy it. When we found out that there are some problems with it, we sent the crew up to fix it, and we could service it. It was not a big problem. But the Webb scope sits at a very cool spot known as a Lagrange point, just under 1 million miles from Earth. So we're not going to be sending astronauts 4 times the distance of the moon to go fix this. We had to do it right the first time. And it was kind of scary because there were about 250 single point of failures that were possible when we opened up and deployed the James Webb scope. Simply put, a Lagrange point where it's sitting is a special spot in space where the gravitational forces of a two-body system and the orbital motion of the bodies balance out each other. So it's kind of like an eddy on a river. It's a little a quiet spot in the gravity. And the James Webb doesn't actually sit at that point, it orbits around it. And that's the L2 spot. Every two-body system has 5 Lagrange points. That Lagrange point, L1, by the way, is where we put our SOHO satellite, which will give us a warning if a really big coronal mass ejection from the sun comes. That'll give us about a 20-minute warning. But we've got people watching the sun, and so we usually get more of that. We usually get a 1 or 2 day warning. But our last time where we can really measure the strength of what's about to hit is at that Lagrange point number 1. Just to review a little simple science, look at the, let's take a quick look at the spectrum so you can understand some of the stuff I'm talking about. We only see visible light, and that's this very tiny spot here in the electromagnetic spectrum. And Hubble did most of its photography imaging in here. A little bit ultraviolet, a little bit infrared, but mostly we saw stuff in the visible light as we see it. The James Webb is entirely in the infrared, the near infrared and mid infrared. And so the images that it takes, we can't see. It gathers data, and what the imagers do is they map the data from the infrared into visible light so we can see all those pretty pictures that we see from the James Webb. None of it is visible to our eyes. So anything that is the lower wavelengths of data that we get, we map as red, and then the higher frequencies we map as blue. And so they just map the infrared spectrum onto the visible spectrum by wavelength, and we see those gorgeous pictures that have come out. This just shows that we've got the spectrum pretty well covered. We see the Hubble, the James Webb, we've got microwave, we've got radio frequencies. This is actually a whole array of telescopes for at very low wavelengths. And we've got gamma ray, X-rays. We've got the spectrum pretty well covered. And sometimes you'll see images that will combine images, that will combine data taken from a bunch of these to really give you some real context. Let me see here. Okay. Now, it's a tradition, or it's become a tradition, that a special image to commemorate an anniversary of doing science with the James Webb, they put out a special image. And this year, they put out the Cat's Paw Nebula. And this is not the image that was released. This is a ground-based image. I just wanted to show you so you could see what it would look like in visible light from the Earth. You've got all kinds of dust and hydrogen alpha that comes out red. This was taken by an astrophotographer, Maicon Germiani, and he's in Brazil. The length of this cat's paw is about 90 light years. That means it takes light 90 years to go from one end of the cat's paw to the other. And you can see 3 little toes there. So they pointed the James Webb at one of those toes. They call them toe beans. I don't know why that is, but I guess that's what you call a cat's toes. And they came up with this image. And this is just, it looks magnificent on the screen, but if you look at it on a computer, it's just an amazing image. This is the Cat's Paw Nebula. The catalog number is NGC 6334. It's located about 4,000 light years away from us. So it's 90 light years across, but the light we're looking at right now is about 4,000 years old. This object is found inside our galaxy. It's not outside. And as I said, this image is taken in infrared light. And that's how it cuts through all of that dust that you saw. That other picture didn't look anything like this, because we need infrared to cut through all that dust that's between us and these stars that are being born. It's a local star forming region, something like the Orion Nebula or the Pillars of Creation. Stars are being birthed here on a regular basis from those dust clouds. Very simply, the dust clouds start to collapse under their own gravity until they heat up enough to fuse hydrogen into helium, and then they light up into protostars. And when the radiation balances the gravity, they reach hydrostatic equilibrium, which is where they sit for most of their time until they burn up all their hydrogen. And then if they're big enough, they'll go supernova eventually. If they're like our sun, they'll just throw off their outer shell and become a white dwarf. But this is where stars are being born with all these gas clouds. There's so much going on here that astronomers get to peer into this cloud-to-star process and look at processes that they think they know, but they don't fully understand. So this is a great lab for them. The tow beam up top here is nicknamed the Opera House. You can see there's a little Sydney Opera House thing going on there. And the source of the blue glow that we see are stars that are still hidden behind the gas that are exciting the atoms in that area and making them glow. And remember, that's quite a distance. It's a couple light years right in that area. Also, you can't see it, but there's a yellow star right in here that's so bright there's diffraction spikes on it, and that's carving out. You can see it's carving out space for itself. You really need to go to science.nasa.gov and take a look at this picture. It's just amazing the amount of detail that's here. To the left of the Opera House, you see this area that seems like it's devoid of stars, but it's not. It's just that the dust is so thick here that our instruments can't cut through them. So that's a really thick chunk of dust there. And over here, these red clumps, these are freshly born stars that are still burning their way out of the dust and the gas, and they're glowing red. To the lower left, we see some stars that are better resolved because they've already burnt through some of the gas, and we just get a better view of them. They burn through that gas either through their solar winds blowing it away, or through the process of photoevaporation, which sculpts dust clouds often when you have a new star. So these hot young stars will have relatively short lifespans, those blue ones. Their life will be measured in millions of years rather than billions of years. They're big, they're hot, and they burn out fast. And as I said, if you look up this photo on your computer, you'll just see all kinds of extra detail. For example, you could almost miss this area right here. This is amazing detail on the NASA photo, the original photo. It's a hot area. You can even see over here, if you look on your computer, there's a bow shock wave, presumably caused by the explosion of gas and dust from a very energetic source. So it's really amazing data that scientists have gotten just from this one photograph, this one image, I should say, and I guess that's why they picked it. If you were here last year when the second anniversary, they released an amazing image called "The Penguin and the Egg," which was just mind-blowing with the amount of detail. Here's one more image before we get into the latest and the greatest. This is an older image, but it's a very famous image. It's called the Eta Carina, the cosmic cliffs, and I put this here to illustrate the difference wavelengths makes. This is a Hubble. The Hubble shot is up top, so that's visible light, and we learn a lot about dust cloud structures and the like. And then down below is the infrared shot from the James Webb, and you can see, first of all, you can see the extra resolution that bigger mirror gives us, but also the infrared itself has cut through so much of that gas and given us a much clearer picture of just what's laying underneath that gas and dust that's between us and the actual cliffs of Carina. So, and then again, remember, imagers colorize that bottom picture. The top one, imagers merely map the data from the Hubble into visible light, since it is visible light. It's a one-to-one mapping. But in the infrared, they have to remap the infrared into visible light so we can see what we're looking at. So let's get on to some of the stuff that was relatively recently breaking. The first one is the Space Telescope discovered a new moon orbiting Uranus. It was first seen on February 2nd of this year. It's designated S2025 U1, and it's so faint it had to be circled in this, looks like my pointer. Well, you can see it, S2025 U1. They circled it. It's a very faint moon. It's kind of small. It's only about 6 miles wide. So imagine James Webb photographing Uranus, which you can't even see naked eye here. You need a telescope just to see the planet. And it's taking an image of something that's 6 miles, something that you can walk across in 2 hours. And although Uranus is 15 times more massive than Earth, because it's so less dense, its surface gravity is only 0.89 times that of Earth. You'd think that you'd weigh, multiple times, but you're actually weighing a fraction of what you weigh on Earth on Uranus on the surface, because it's so less dense. So you could walk that 6 miles in record time if it wasn't for the negative 320 degrees Fahrenheit temperature, which probably slow me down a little bit. So Matthew Tescanero, a member of the research team and a senior research scientist at SETI, said no other planet has as many small inner moons as Uranus. He also said that the complex relationship between all these small moons and the rings hints that that Uranus must have had a chaotic past, and that's for sure. The planet itself rotates on a 98-degree tilt from the orbit that it goes around the sun in. So it seems like it's on its side, and even years ago, the theory was that something big must have smacked into it, and maybe that's why it has so many little moons. That, some of that debris has flown off. There's nothing I can do with that weird noise. Oh, okay. Here's another one for you. This is just a drawing, so it's not as exciting. But near-Earth asteroid 2024 YR4 was discovered in December of 2024, and it caught the attention of the whole worldwide planetary defense community, according to NASA. And because it looked like that asteroid might collide into our moon. And there was a great uncertainty on the trajectory, and the James Webb has decreased that uncertainty, but not so much in a good way. We used to think it was like between 131 and 295 feet, like a large skyscraper. We now see it's more like between 174 to 220, so it's on the large end of the scale. So this asteroid here is about the size of a 10-story building, and it's going to come very close to the moon on December 22nd, 2032. So not too far away. Originally they gave it a 1.7% chance of hitting the moon, and with our James Webb space observations, that's increased to 3.8%. So there's still a 96.2 chance that the asteroid's going to miss the moon. We're just going to have to stand by and see. And in the small chance that the asteroid does hit the moon, the asteroid's not big enough to affect the moon's orbit, which is a good thing. So to me, the worst case scenario isn't it hitting the moon. To me, the worst case scenario is it hitting the dark side of the moon, where astronomers can't watch the impact. That would really stink. Because the moon, the dark side, never turns to where we can see it. Back in 97, comet Schumacher-Levy broke into 20-some pieces and hit Jupiter on the side we couldn't see. But then Jupiter turned around, and we could see these Earth-sized plumes of smoke on the face of Jupiter as a result of those comet strikes. So anyway, that's kind of interesting. Anyone have a guess what that is? What's that? It's actually the north pole of Jupiter and aurora activity. We've known that there's auroral activity on Jupiter for quite some time. We've had some pretty cool pictures of it. But the James Webb has given us a whole new view of it, and just how powerful those auroral activities are. We have aurora on Earth. We call them the northern and southern lights, and it's basically particles carried by the solar wind hit the magnetic lines or the magnetic force of Earth, and Earth slams those particles down into the north and south poles, and it excites those atoms, and they glow. And that's what's happening here as well with Jupiter. But Jupiter has an additional source for those auroras, in that its closest moon, Io, is the most volcanic object in our solar system, and it spews out a ton of sulfur. It actually gathers as a toroid around Jupiter, and so Jupiter's magnetic field also catches that from Io and slams that down into the north and south pole, and so we have even more material than would otherwise be just from the sun causing the aurora. And another thing is that the NIRCam, which is the near infrared camera on the James Webb, can show changes in small amounts of time. And scientists used to think that changes in the aurora used to occur over 10 or 15 minutes. But now they're seeing what one scientist described as fizzing and popping in sometimes by second. So they're really amazed at just how much change is coming on and how quickly it is happening. So these studies give insights into not only Jupiter's aurora, but Jupiter's atmosphere and how it's heated and cooled. So there's a lot of good information to be had there. There's another one of our planets, Neptune. And in March of this year, James Webb captured auroral activity on Neptune for the first time. And on the left is a color-enhanced image from the Hubble. And then what we've done is we've taken the same image and just added James Webb data. And you see the cyan on the right-hand side. That's the auroral activity. The white is clouds that are picked up in the image. And usually you would expect it to be on the top or on the bottom, right, the North or South Pole. But remember, I said Neptune, but in Neptune, it's actually over to the side. It's pretty interesting. So we have now confirmed proof that there's auroral activity on Jupiter, Saturn, Uranus, and Neptune. All of the 4 gas giants exhibit auroras, and we have images of that. So this is a ground-based photo. I just want to show you the area that we're looking at. I was lucky enough to go to New Zealand and see this site in March of this year and take some astro photos, which I'll be showing in 2 or 3 weeks. I'm going to do a little talk on smart telescopes. But the area of our interest is on the left, Alpha Centauri. And for anyone as old as I am, that's where the spacecraft Jupiter from Lost in Space was heading to Alpha Centauri, the Robinson family, to settle on a planet in Alpha Centauri. Alpha Centauri is actually a 3-star system. There's a binary system, Alpha Centauri A and B, and then Alpha Proxima goes around that binary system. And Alpha Proxima is the closest star to us. It's a red dwarf. So it's magnitude 11.1, so it's very dim. You can't see Alpha Proxima with naked eye or even binoculars. And because it's dim, though, there's not a whole lot of glare from it. And we've already have 2 confirmed exoplanets orbiting Proxima, and we also have 1 that's disputed and awaiting confirmation. And that's at about a distance of 4.2 light years from us. Now, Alpha Centauri A and B, that tight binary system, they are much brighter, and the 2 stars are only separated by 2.1 billion miles, which is basically the distance from us to Uranus, the planet Uranus. So imagine instead of a planet at Uranus, there was another star there. That's what this star system looks like, and they're very bright. And in another 25,000 years, Alpha Centauri A and B will be the closest stars to our system, because Proxima goes around A and B every 550,000 years. So pretty soon it'll be further from us than A and B will, and they'll be the closest stars to us. And then every 80 years they'll switch. A will be closer than B, and so on. But anyway, they're really bright and hard to image, or especially if you're looking for a very dim exoplanet. Centauri A is the third brightest star in the night sky, and confirming any exoplanets around that star is a very, very difficult situation, especially when you use the James Webb, because the James Webb was designed to be so sensitive that it could pick up galaxies billions of light years away. And so now we're pointing it at this really bright star, and this just gives you an idea of how bright it is. On the left is a ground-based telescope that shows A and B as just one really bright light. In the middle, we see Hubble telescope was able to split those 2 stars, so you can see the binary aspect of it. And for this target, according to John Beichman, who was part of the team that imaged it, they had to come up with a special procedure just to photograph, just to look for any exoplanets. And what they did was they used what's known as a coronagraphic mask. And on this picture on the right of the Hubble, that black circle with the star is a coronagraphic map. So it's like making a artificial eclipse of that star, so that the optics of the James Webb can look past the star and see if it picks up any exoplanets. So here's another panel. The panel on the left shows the glare from Alpha Centauri A and B. And you can't even see, they're so close together, you can't even see the star, but you can see two sets of diffraction spikes. A bright star will make a set of diffraction spikes. This binary system makes two sets. So that's just how bright it would look if we just pointed the James Webb at it without a mask. The middle panel shows A and B with the coronagraph over A. But there's still a lot of interference, not only from light that scatters around the coronagraph, but also from the James Webb itself. It has some struts that hold the secondary mirror in place, and some other structural changes, structural things in place. And so what scientists had to do was calculate the scattering of the light through those mechanical objects, and they came up with an algorithm that subtracted that light from the middle section, and they finally came up with an area where they could actually see that exoplanet. And by the way, an exoplanet is what they call any planet that's outside of our solar system. So any planet that resides around another star is known as an exoplanet, and we found about over 1,000 of them so far. So they accomplished this in August of 2024, and then they went back in February and April, and they couldn't find the planet. They looked all over, they did the same procedures, and they couldn't find the planet. So a team of astrophysicists ran a bunch of simulations, assuming that the planet's orbit was stable enough not to be flung out of the system. And they determined that half of the simulations ended with the planet being too close to the star at this time to be detected. So it was too close to be detected in February and April. This is it's hard to even describe what a tough problem this is. There's something called the three-body problem, and it's just trying to figure out what the effect of three stars or three bodies are on each other as they orbit around each other. And it takes massive calculations, and the best you can do is just come up with a bunch of simulations. You can't solve the equation with one answer. So it's just amazing that they were able to get that done at all. This is just an artist's rendition of what that gas giant could look like. It's probably the size of Saturn, and in this picture on the left is Alpha Centauri A, on the right is Alpha Centauri B, and in the middle is our sun. And as I said, it's an artist's conception of what that planet would look like. Just a quick quote. If confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It's also the most similar in temperature and age to the giant planets in our solar system and nearest to our home, Earth. Its very existence in a system of two closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. So, to people who study exoplanets, this is a big deal. And also, that exoplanet lies in the habitable zone, also known as the Goldilocks zone. It's not too close to the star, and it's not too far from the star. If it was Earth, it would be in that zone where life could prosper. The only problem is a gas giant could not spawn life as we know it on Earth. So if there is life on that exoplanet, it's a form that we have no idea about, because it would have to be like nothing that we've seen here. And then finally, I would just science fiction I like to read once in a while, and I just recommend this book by Cixin Liu called The Three Body Problem. Is about aliens that live on an exoplanet about 4 light years from Earth in a 3-star system. Sound familiar? And it's a great read. It's a lot of great hard science in there, and basically they find out through a rebel alien on the planet that they're going to be invaded, and they're coming over as fast as they can, and it's going to take 400 years to cross the 4 light years, and so they have 400 years to prepare for it, and that's what the 3 volumes are. And it's a real fun read. And if you're too lazy to read, shame on you. But Netflix does have a series they just came out with called The Three Body Problem, based on these books. I won't look at it until I'm done reading that 3rd volume. I'm about halfway through volume number 3. So I still have a ways to go. But I understand that the series is pretty good as well. I just can't recommend it myself because I don't know it. All right, next. This is called a jellyfish galaxy. And this is not a Webb image. This is a Hubble image, but it's a great example of what we're talking about. Let me see. Aha. So our knowledge of galaxy evolution is growing on a bunch of fronts, especially when we're looking way out there towards the beginning of the universe. But these are some interesting galaxies only recently discovered. They're a class of galaxies that seem to drip tentacles of star-forming material. And in clusters of galaxy, the space between the galaxies is not exactly a vacuum or void. There's hot gases and other gases that will cause drag on a galaxy that happens to be passing through the area. And that's what's happening here. This galaxy is passing through, and the drag is causing some of the star-forming material of dust and gas to drag out and kind of like follow behind the galaxy. It's a process known as ram pressure stripping, and what it does is it prematurely slows star production in a galaxy. We've seen evidence that galaxies in clusters stop forming new stars earlier than galaxies that aren't in a cluster, but the mechanisms involved are still not well understood at all. So that's a great example of a jellyfish galaxy. This is the one that James Webb discovered, and we've circled the tentacles that we think are tentacles. Ian Roberts of Waterloo University was pouring through data that was released by the James Webb Space Telescope, and came up on this image, and thinks that this is probably the most distant jellyfish galaxy discovered so far, with an estimated distance of 12 light years. You know, a lot of discoveries and a lot of papers are written by scientists who wait for specific data from surveys to be released, and then they pour through the images looking at what they can see. In this case, you know, we've never searched for this specific type of galaxy, a jellyfish galaxy. So we really don't know how common they are or how many exist, except for the ones that we've come across. No one's done that project yet. Roberts suspects that these have a relatively short lifespan, cosmologically anyway, and that it may be unusual to capture some of these on an image just because they have a short lifespan. Let's see how we're doing on time. Okay. So the data from the James Webb scope is really shaking up theories on galaxy formation. What scientists thought they knew, they're not so sure now. And you know, one of the things they're being surprised at is as they look deep into space, like within a few 100 million years, or call it less than 1 billion years after the Big Bang, they're surprised at how many well-developed galaxies they're finding. The current theory was that they shouldn't be that well developed, that it would take quite a while for them to develop, and that the heavier metals, anything heavier than helium, it's all called metals by astronomers, you know, would have to wait for a couple supernovas to fuse hydrogen and make those elements. And yet they're finding them earlier than they would have expected. And they're finding black holes earlier than expected. You know, right now the common wisdom is that when you have a really big star, say over 60 masses of the sun, when it goes supernova, it leaves a black hole behind. And then that black hole starts eating up whatever it can find, whatever's in the area. It starts eating it up until it gets bigger and bigger and bigger. And so that implies that quite a lot of time has to pass for this black hole to get to, you know, first of all, to even be formed, and second of all, to get to as big as it is. So this image, although it doesn't look that important, may help with some of the confusion that scientists are having. It's known as the Infinity Galaxy, and NASA's website states that the object is a result of two colliding spiral galaxies. And you can see the nucleus of each one. They're separated, and you can see those yellow spots. Those are the nucleus of those two galaxies, and each one of those has a black hole. We could tell that there are a black hole in the center of it. But the real surprise is that in the middle between the two, there's that kind of greenish area. There's glowing hydrogen that's been stripped of its electrons right between those two galaxies. And astronomers have detected a 1 million mass black hole that seems to be embedded within this large swath of ionized gas. And they suggest that the black hole might have formed there through a process known as direct collapse, which means that this black hole was not formed by a dying star that goes supernova. It was formed in a way similar to the way stars are formed, that this immense amount of gas around it collapsed and formed a black hole instead of an ignited star. It gives me intellectual constipation just thinking about it. But instead of the black being formed from the explosion, it's formed directly. And if that's the case, it would take less time for black holes to form. So the jury's still out. This is brand new science. Papers are just coming out. And of course, if you YouTube this, you're going to find everything from some good scientific explanations to some real wackos talking about it, because it's very unusual for a black hole to be between two nuclei instead of in the center of a galaxy. So if their theory is correct about the way this is formed, you're looking at something that's never been seen before. Again, this object was discovered by two researchers just pouring through the data. In this case, the JWST's Cosmos Webb survey. That's the previous image with just, we talked about combining information from telescopes. And so this puts a map of energy that's picked up on a very large radio wave antenna on the Earth and overlaid, and you can see that the lines line up perfectly with the center of the glowing gas detected in the infrared between the two nuclei, and the map shows us the intensity of the energy in that area. Okay, let's get into even more tenuous theories birthed by JWST. And I'll speed this one up, but this is a bunch of galaxies, and it's found that in a survey containing 263 galaxies, where the images were clear enough to detect the direction of rotation, it looks like about 2/3 of the galaxies rotate in the same direction. And we would expect the current theory of an isotropic universe, which is pretty much the same everywhere you look, would say that it should be closer to a 50-50 split in the rotation. So this is indicating the red circles are fewer, and they rotate the same way that our Milky Way galaxy does. The blue is the majority of galaxies, and they rotate in the other direction. This is the larger map. And then I actually found, if you're a real nerd, you can actually find a map. This is a picture of each one of the galaxies that rotate in the same direction. And you know, doing the math, I count. Each one is numbered, and I did the math, and it's about a 60-point-something% go in one direction, and then 40 in the other. To me, I'm not that impressed, but it's enough that people are wondering if we were, if the universe was birthed inside of something that was rotating. And then that has spawned all kinds of theories. One theory is that maybe we're inside of a black hole, and that we were birthed inside of a black hole because that would be rotating, and we would have been born inside of that. You go to YouTube and you'll see all kinds of crazy stuff riffing off of this discovery. All they had to do was say maybe we were born in a black hole as one of the theories, and people just took off with it. There's all kinds of craziness out there. But anyway, that's another interesting discovery that just happened over the last few months. And finally, I'll just show you we have now found the furthest galaxy yet. You know, before James Webb started imaging, just before, that's only 3 years ago, we confirmed a galactic candidate from the first 500 million years of the universe. So like 13.3 billion years old. And that was GNZ11, which I actually presented as the oldest galaxy we know of a number of years ago. And although it's still a very distant galaxy, it isn't even in the top 10 oldest galaxies now that James Webb is out there photographing galaxies. It's been knocked down further down the list. And we find that these ultra-distant galaxies are about 100 times more abundant than we expected. And this is the current record holder. It was announced on May 16th. And now here in August, it's still holding the record. So it's the undisputed king so far. It's got a redshift of 14.44, which puts the galaxy within 280 million years of the Big Bang, which is just mind-blowing. And the MOM survey stands for Miracle of Miracles, and it was initiated to determine whether the bright early galaxies really were as far away as we thought. And after re-imaging and analyzing this galaxy's light, the research pronounced MOM Z14 a miracle and not a mirage. So you now have seen the furthest galaxy. By the time you come back for my fourth talk, I'm sure that it'll be knocked out. A lot of this stuff that has to do with how quickly the universe is expanding, has to do with what's the final end of our universe. The three theories. You've got the big crunch, where we get out to one point and then we just reverse the whole process and crunch together. That's the least likely. You've got the big rip where the energy just ends up ripping up the entire universe. And then the big freeze is just things move away from each other. This is the most likely. They just keep moving away from each other at the expansion rate, and let the law of thermodynamics take place, and just lose energy after the black holes evaporate in a googly years. That's one with how 100 zeros after it. The universe will be pretty much dead. So that's it. There's quite a bit of circumstantial evidence for the big freeze, but I'll leave you to look at for yourself. I don't want to take any longer. It's a gorgeous night, and we want to see the Ring Nebula and all kinds of good stuff. So with that, we can open it up for questions.
Helps if I turn my mic on. So thank you, Walt, for another great talk. Thank you all.
Thanks.
We are going to be doing a question and answer session. So before that, I do know a couple people snuck in after the first safety briefing, and unfortunately that has to be unescapable. If you need to use the restroom, that is the porta potty in back. It is big, it is blue, it is illuminated by red for ease of finding in the dark. We also have a museum area and gift shop open, and I now have someone in there, so feel free to check that out. You don't have to wait for me. Each of the sheds you saw coming in houses its own telescope. The ones where the roofs are rolled off are open and have a volunteer. That static is me every time I move. Roofs rolled off, volunteer in there. Feel free to ask some questions, ask what they're looking at. When we do go to leave, we are using our headlights because we prefer not getting run over, and ain't no one need those medical bills, so let's try and keep that at a 0 roadkill rate.
Oh, wow.
We aren't playing Frogger. That being said, any flashlights, cell phone lights that we use to move around in the dark, do keep those towards the bottom, towards the earth. So, with that, for people here, if you have any questions, you're going to raise your hand and wave it about like you just don't care. Mostly because in the night, because I've been monitoring online chat, I have no night vision. And my night vision now is based on movement like the Jurassic Park T-Rex. So you will cease to exist if you put your hand down and stop moving. It's a problem. I have an appointment sometime, but no time soon because too busy. Online people, you get it easy. You just get to type in chat. So, want to open it up? Anyone have a question out here? And I will hand you the mic so other people can hear.
Well, I don't think I need it.
Online people need to hear the question.
There's so many photographs being taken. I was just wondering if they have AI looking at them so that every time another photograph is taken, they're looking for any change, no matter how minuscule, that it might be detected, and then there might be some theories developed about whatever the noted change is.
Yeah. First of all, you won't hurt my feelings if you go out and look at the stars. That's a given. Yeah, they do use AI to do those searches. You know, it used to be a blink comparator, right? Clyde Tombaugh found a Pluto by looking at photographic plates and looking to see what moved and what didn't. And now they can do that with AI. AI is used in all. I even have a telescope that uses AI to denoise the images, to take some of the background noise out. So AI is being used widely in the field of astronomy to analyze data, to clean up data, to bring some of those pictures and save hundreds of hours of processing time. So yeah, it's very widely used.
It's a tool, but I still think they have people reviewing anything where it flags, just because the tool is only as good as the people who make it and use it.
Yeah.
Emphasis on use it.
Well, some of those
So-
things, just like those two spiral galaxies that were merging, and there was another black hole in the middle. AI is not going to pick up on that. I mean, I guess, I mean, there's no other data to train it on. That's like a first. It takes someone who knows astronomy to look at that photo and say, "Wow, I think I've got something here." And there's been a number of discoveries that we talked about here that you really need someone to know. And maybe in the future that'll change, but right now, yeah, you still need people to take a look at the data as well.
Right. Our first online question was, are you guys doing the last Saturday Halloween special this year? The answer is that is the plan. We do incur on the last Saturday of October is the last time of the year before it gets real snowy, icy, unpleasant weather where no one wants to come up. And since it's so close to Halloween, we encourage people to come up, enjoy the night sky with us in Halloween costume.
It's always fun.
I know a lot of times, occasionally our volunteers will bring up candy or other goodies. So I can't guarantee candy or other goodies, but a lot of us will be in costume. I'm already starting to plan that, out my outfit for that night. Right, was there another question out here? Keep in mind, I'm kind of just motion-based. But right now I feel like one of those kind of defunct lights you get from Home Depot where it's like, is that something? Oh, no, it was nothing. Right, so our next online question was, isn't the dark side of the moon a misnomer? That side does see the light. We just never see that side because of the rate of rotation matching the rate it orbits the Earth.
Yeah, we never see it. That's why it's dark to us. The moon is tidally locked. It does see light, but we don't see light on that side. We see on full moons, sometimes we see a little more or a little less, depending on our axis and where the moon's at. But yeah, we never see the dark side, but it does
I
get some
think
light.
a lot of people have switched over to saying the far side
Far
of the
side.
moon. Of the moon.
I think of a comic strip when you say far side.
Yes, and they have all the cow tools over there. All right. Like I said, if you have any questions, do feel free to raise your hand, and I will bring you the mic. Because a lot of times, if someone might have the same question, just not be as brave enough to say it. Online people, I do want to encourage you, if you do have any questions, do get those in. Just because, and I say this now, because by the time they hear it, we're already 2 minutes into the future, because that's how stream delays work. And someone asked what I was doing because they saw me kind of showing something. I'm chasing toads, keeping toads out of the building. It is that time of year where light attracts bugs, bugs attract frogs and toads, and I do not want them in the house because that is where they will not survive. I prefer them to survive and therefore not be in the house. All right. Last call. Bueller. I hear a lot of crickets.
You don't want to
Bueller?
hear that when you're a speaker. But
Well,
yeah,
we don't really got a choice in the state park. We're
That's
kind of
just
in
it.
their home. Right. So once again, I do want to thank you, Walt, for another great presentation. And I want to thank everyone who has joined us not only here on site, but also in our online chat on YouTube and Twitch. Until then, like I said, check out our website. You'll find a whole ton more information. Follow us on our social media. Hit those like and subscribe on our streaming platforms. And with that, everyone have a great night, clear skies, and good seeing.
yeah, take a look. There's going to be some gorgeous stuff out there. Thank you.